A semiconductor material is one whose electrical properties lie in between those of insulators and good conductors. Examples are germanium and silicon. In terms of energy bands, semiconductors can be defined as those materials which have almost an empty conduction band and almost filled valence band with a very narrow energy gap, of the order of 1 electron volt separating the two.
An intrinsic semiconductor is one which is made of the semiconductor material in its extremely pure form. Examples of such semiconductors are pure germanium and silicon, which have forbidden energy gaps of 0.72 electron volts and 1.1 electron volts respectively. The energy gap is so small that even at ordinary room temperature, there are many electrons which possess sufficient energy to jump across the small energy gap between the valence and the conduction bands. Those intrinsic semiconductors to which some suitable impurity or doping agent or doping has been added in extremely small amounts, about 1 part in 108, are called extrinsic or impurity semiconductors. Depending on the type of doping material used, extrinsic semiconductors can be subdivided into two classes: I, N-type semiconductors and E, P-type semiconductors. This type of semiconductor is obtained when a pentavalent material like antimony Sb is added to pure germanium crystal. As shown in Fig. Below, each antimony atom forms covalent bonds with the surrounding 4 germanium atoms with the help of 4 of its 5 electrons. The 5th electron is superfluous and is loosely bound to the antimony atom.
This type of semiconductor is obtained when traces of a trivalent like boron B are added to a pure germanium crystal. In this case, the 3 valence electrons of boron atom form covalent bonds with 4 surrounding germanium atoms, but one bond is left incomplete and gives rise to a hole as shown in Fig. Below. Thus, boron, which is called an acceptor impurity, causes as many positive holes in a germanium crystal as there are boron atoms, thereby producing a p-type P for positive extrinsic semiconductor.
In a piece of pure germanium or silicon, no free charge carriers are available at 0 kelvins. However, as its temperature is raised to room temperature, some of the covalent bonds are broken by heat energy and as a result, electron-hole pairs are produced. These are called thermally generated charge carriers. They are also known as intrinsically available charge carriers. Ordinarily, their number is quite small. An intrinsic of pure germanium can be converted into a p-type semiconductor by the addition of an acceptor impurity which adds a large number of holes to it. Hence, a p-type material contains following charge carriers. A large number of positive holes, most of them being the added impurity holes with only a very small number of thermally generated ones. B. A very small number of thermally generated electrons, the companions of the thermally generated holes mentioned above.